Great. Thanks so much for the nice intro and for inviting me. And thanks everyone for attending. Hopefully we'll all see each other in person before too long. So I want to tell you about a little bit of work I've done about how quantum and classical computers can work together to solve problems. And this partly was motivated by my thoughts about many quantum algorithms are designed with input models that are not always the most directly related to problems. So actually, Umesh mentioned the linear system of equations algorithm, and I've spent a lot of time since then thinking about how you might use it and what are the barriers to using it, or the challenges. What additional things need to be solved in order to use it. And it caused me to realize that we should be thinking about quantum algorithms. It's a very important detail is to organize them by the type of input. So we often think about classical algorithms as having what you might call the standard input model. So the input is a string, written on the tape of a Turing machine or on a hard drive or in RAM. And the output could be a bit or it could be a string, not much difference. And a lot of the cleanest to state problems are often in this model, like factoring. We all kind of agree on how the input is described and how the output is described, and it's all very satisfactory. Combinatorial optimization, like a 3-sat instance. You want to satisfy as many clauses as you can in the 3-sat instance. We all agree how the instance is written down, what the answer looks like. Okay, maybe this is quite hard to solve, but at least maybe we can talk about some approximation algorithms to it. At least the input and output is quite clear. But to design quantum algorithms, we often want to work with other models. This is often a very intellectually fruitful thing to do. For example, the oracle model, maybe the input x1 through xn, where our access to it is not as a string written down, but we have implicit access to it given by way of a subroutine or an oracle that we can query in superposition. And this is the way that Grover is defined, the NAND tree problem, the collision speedup, as well as exponential speedups, like the hidden subgroup problem and the welded tree problem. And sometimes these overlap. So one thing that Shor did was he showed, or rather this Kataev's version of it, showed how the hidden subgroup problem over a billion groups could be solved efficiently. This is an abstract problem that doesn't tell you what the black box function is. It just says, suppose you have a black box function that you can compute that has this particular kind of symmetry, then a quantum computer can find the hidden subgroup. It takes additional work to go from that to a factoring algorithm. So the HSP, is useful by itself, but not immediately sufficient. And then there are other ones that are another direction we can go in on a quantum computer is we can say the input can be given as quantum data. So this is what happens for the linear systems algorithm, is the input is given as a quantum vector, and this is what enables the big speedups. The Fourier transform is another story. You have a classical and a quantum Fourier transform, and they are incomparable because they operate on different types of data, right? The classical Fourier transform operates on a list of numbers that you might have in RAM. The quantum Fourier transform operates on the amplitudes of a wave function. Neither one is a substitute for the other, right? They're really achieving different things. And there are many algorithms in this nature that are very useful, but often useful as subroutines, right? The quantum Fourier transform doesn't solve the problem by itself. It's an element in these other things like factoring. And finally, you can combine the quantum data and the oracle model to get the quantum oracle model, where you're given black box access to some unitary U. This too can be useful, but you can tell a pattern here. Oftentimes, this is part of a subroutine that we'd like to use building towards something in the standard model where we have a conventional input and a conventional output. And in fact, all of these show up in factoring, right? So phase estimation is something in the quantum oracle model, the quantum Fourier transform, something in the quantum data model, hidden subgroup problem is in the oracle model. All of those are different ingredients that Shor combined to achieve factoring. All of them are intellectually great accomplishments on their own, but to make them useful, you want to go a little bit further. So, oops, wrong way. So what about Grover's algorithm? This is one of the most basic, earliest algorithms. You can explain it very simply. It's a beautiful picture of what you can do with a quantum computer. It's beautiful because it's like, it's like climbing a smooth wall. There's just nothing for the algorithm to grab onto. And yet you can go from classical n to quantum root n. And the original title of the paper was confusingly titled A Quantum Mechanical Algorithm for Database Search. And somewhere between the archive and PRA, this got changed, but it's super confusing because there's really nothing to do with databases. It really is, if I have a function that I can compute, and the truth table of that function, f, f of 1 through f of n corresponds to my bit string, then I can find a marked element in that implicit database of function outputs. And that is, that's, I think, the right way to think about Grover's algorithm. And since then, of course, we found many similar quadratic or polynomial speedups for many other unstructured or semi-structured search problems, like maximizing a black box function, approximately counting, like adding up, integration, etc. Finding collisions, finding triangles in graphs. Game trees are like NAND trees. We can speed up simulated annealing roughly quadratically. So many things don't rely on very much structure of the problem. We can get these kind of quadratic speedups. But it involves an oracle, right? This oracle is a subroutine that takes in an index that you want to query and returns x sub I. And if this is a picture of a data center, that is not something that is not the same as an oracle. We cannot query the data center in superposition. You cannot use Grover's algorithm to search the data center, nor would you want to, right? If you wanted to just find a record in your data center that matched some criteria, you should probably, well, if you're not building an index, you should probably do it in parallel. If you have a gazillion hard drives, you probably have a gazillion over 4 CPUs. And so you could just distribute your query to all of those. And that would make more sense than doing some kind of sequential search. Now, one proposal for getting Grover to work on a large data set is to build a quantum RAM. But as a theorist, I would be a little embarrassed to do this because my job is already easier. I see some experimentalists on the call. I already have a job that is way easier than the experimentalist job. And I think, for me to merely ask the experimentalists to build a conventional quantum computer with 1 million error-corrected qubits, I want to just limit my demands to that and not ask them for any kind of additional hardware requirements, at least not until I've done a little bit more work on the algorithm theory side. So I think a quantum RAM would be great, but as theorist, I have some obligation to see what I can do without it. Okay, so what can I do without it? Let's suppose that I have my input, x1 through xn, it lives on one of these kinds of devices. I guess that's already a little bit of an old-fashioned kind of hard drive. And I want to turn it into a quantum oracle. I'm still looking for a good illustration for that. If anyone has ideas, let me know. How can I do it? It's not so easy. One answer, which is somewhat unsatisfactory, is if I have a quantum computer, which is, since I see Dan here, it's going to be an ion trap computer. Got a bunch of ions. They're getting blasted by lasers, or maybe there's some magnetic fields that are changed. These are controlled by the pulse generator, which talks to the FPGA, which talks to the laptop, which maybe is connected to the hard drive. So what the laptop can do is read the hard drive, read one record, figure out what x sub 1 is, figure out a bunch of quantum gates that will perform this controlled operation. If this first register is 1, then add x sub 1 to the second register, that's unitary, and just do that n times sequentially. So the quantum computer never has to directly touch the hard drive, right? There's no weird data model here. It's a completely conventional kind of data model. It could work for a very small quantum computer and a large hard drive. It works, but there's a terrible cost to it, which is this order n cost, right? So if I have to do an order n, if every single query to my database takes time order n, that's going to wipe out the speed up for a lot of Oracle problems. So what can I do? Well, I can posit the existence of a QRAM, which, that solves some problem but creates others. Or I can do what Peter Shor did. I can say, well, this x1 through xn, I just need to come up with an efficiently calculable function. So Shor came up with modular exponentiation. F of I is a to the I mod n. If you can come up with that function and realize that solving the hidden subgroup problem there solves your problem, then that's great. But as we've seen in the 25 years since Shor's algorithm, those insights do not come along every year, and certainly they don't apply to every data set, right? Some data sets correspond to the truth tables of efficiently calculable functions. Some of them are just, a big pile of cat images you have from the internet, and there's no reason to assume that such a function exists, or if it did, how you'd ever find it. So instead, although there is actually a possibility of trying to use some sort of generative model to create such a function, and I think there's definitely room for progress there, which is I think another possible direction to take this work in. What I'm going to talk about are ways that we can reduce the size of the data set and still get a meaningful speed up. So I'll talk about problems that are fairly natural problems like clustering, Bayesian inference, and saddle point optimization. So fairly general problems where you can make progress by reducing the size of your data set, and where you can usefully use a quantum computer without any kind of weird data assumptions. So let me be a little more concrete about the type of problem I want to solve. So one example of such a problem is maximum likelihood estimation, or you could also say maximum a posteriori estimation if there's a prior. You have a set of models Y and a data set X. And you assume that the data set's drawn from a bunch of data points that are independently sampled from some distribution that's given by your models. You want to find the most likely Y, the most likely model Y that could generate that data set. That means maximizing the log likelihood. So the chance of seeing point X given Y is P of X given Y. The log of that is F of X given Y, sort of this measure of a score of how good is Y given, how well do X and Y fit together. You want to sum that over your whole data set because this is log likelihood, and maybe add a term R of Y that represents how much you prefer some models over others, even before you've seen any data, maybe because you have a prior or because some models are simpler than others. So this is a basic and general problem, pretty easy to relate to applications. How can a quantum computer speed this up if you don't know anything more about the structure of it? So as a math equation, X and Y appear almost symmetrically. Okay, one of them is a max and one of them is a sum, but you can get Grover speedups for both of these. However, X lives on a hard drive. It's a data set. We do not have superposition access to it. Whereas Y, for many classes of models, is a synthetic data set. It's like the truth table of a function. It's something that we can easily get superposition access to. For example, if it's a clustering problem, Y could be the set of all possible clusterings. And so you would enumerate all the possible centers and weights or covariance matrices of these clusters. That's something that you don't need to explicitly list all of them. You have an implicit list of, you can get functional access to it. And so in our model of a classical computer controlling a quantum computer, you can, if you wanted to do a Grover, see what your Grover speedup was, then your outer loop would be the search over Y. You could get a square root speedup there, but your inner loop, you'd still have to step over the whole data set, right? The inner loop where you sum over X, you would not be able to get a meaningful speedup. And this is, and you can imagine doing better than Grover, by the way. I'm going to use Grover for concreteness because it's always bothered me that I don't know how to use Grover to solve these simple optimization problems. There are possibly better optimization algorithms than Grover's, like maybe adiabatic will turn out to be really great, or, QAOA or something else. That is, whatever you use, that's going to improve the dependence on Y. If you're lucky, maybe it'll improve it exponentially, who knows? But the more it improves the dependence on Y and leaves X untouched, then almost the more unsatisfactory it becomes because your runtime is still dominated by this large data set. So one question to get these algorithms to work well is, can we reduce the dependence on the size of X? Before I talk about how to do this, any question about the model, about the problems that we're trying to solve?
Yeah, so I see a question in the chat, which let me try to rephrase a little bit. It sort of says, well, these Ys are actually usually very structured. It says they're continuous, but there's also structure in them. And so just getting, even if you discretize, getting square root of Y may not be enough, but maybe that you have some effective dimension. So do you have something to say about that?
Good, right. Yeah, very good question. So let's suppose that your set Y is, let's say, the weights of some neural network. Of course, that's continuous, and you might try to solve that with gradient descent. And when you do that, you find that you end in a local minimum. So one thing that you might do on a classical computer is just restart a gazillion times. And what this amounts to is searching over your local minima. And so whenever you're doing something where you pick a random starting point and then you run some short algorithm, like you do a brief gradient descent and then you evaluate, and you're just trying that over and over and over again, that is amenable to Grover. So what you could do then is you're not literally Grovering over every single weight in the neural network, because that would be wasteful. You actually gradient descent is a good algorithm, but you're Grovering over starting points for gradient descent and then running a short gradient descent. So that's one answer. Another answer is, Grover is not the only algorithm. There's this beautiful algorithm that came out of Maryland for escaping saddle points on a quantum computer, that gives you another sort of tool in your optimization toolkit for optimizing over non-convex functions. So there could be things that you do that are better than Grover. Yeah, you could also search over the hyperparameters. I opened up the chat window so I can see these things now. And kind of whatever you're doing to speed up your search, if the inner loop has a dependence on the full data set, that is going to kill you no matter what, right? So you can imagine, I'm just kind of saying Grover to give you something concrete to sink your teeth into, but definitely depending on the problem, there may be many, many better ways to do it. And actually later on, I'll show you an example of something where you can, I'll come back to this where you can definitely do better than Grover. Basically, Grover is like a square root speedup of brute force search. And there are square root speedups of better algorithms out there as well. So sometimes we have a square root speedup of what's possibly the best classical algorithm. And Grover certainly is not that. So we'll see that example. But basically, I'm saying Grover to give you something to sink your teeth into, so you can appreciate the data issues that arise really in any of these optimization algorithms. Another question was about what is the relation between X and Y. Well, at one level they're decoupled, like you have a space of models that you're searching over, like all possible clusterings, and then X is just your set of data points. So basically, Y are the possible models, and then and then you're assuming that there exists some model, and then the data set X is sampled from the distribution corresponding to that model. Now, maybe in practice, the more data you have, the richer the family of models you can search over. So there may be some kind of implicit dependence like that, but in general, there doesn't have to be a direct relation between them. Yeah, thanks for the questions.
Aram, Henry Ewan asks if the search over the data set is in the inner loop and the outer loop is searching over Y in superposition. Doesn't that mean X is being accessed in superposition?
Yeah, so what's happening to X is something like this, except what we're really doing is we're saying conditioned on Y, add f of X comma Y to your running total of the log likelihood, and then iterate that over all values of X. So when I say accessing X in superposition, what we're not doing is we're never making a superposition of queries to different values of X, right? So different data points we're never querying at the same time. The data point, the X that we're querying is a classical variable. You know, the hard drive is like it's on that platter, and the head of the hard drive is pointing to one record on the platter, and that is a classical thing that we're querying. And then we're sequentially stepping through all the values of X. Hope that answers that question. Yeah. Good. Yes, it's okay. So so what can we do? You know, having to wait to go through every record on the hard drive while my quantum computer is decohering makes me very sad. So I don't want to spend all that time doing that on the inner loop of my quantum algorithm. It's also, you know, it's the quantum computer. It's like having your quantum computer spend time doing arithmetic, right? Like doing like a 32-bit multiply on a quantum computer is very sad to do because there's no advantage there, right? The advantage comes from other parts of the circuit. So you want to spend as little time as possible on the stuff that is not bringing you quantum advantage. So one thing you can do is approximate your big data set by a small data set. That's called, this idea came from the computational geometry, and this has spread to machine learning. It's called taking a coreset. And I've illustrated this for the example of clustering, but it's, the coresets exist for many different problems. And the idea is that you approximate your original data set X with a subset X prime. Or I should maybe have written X prime comma W, because I also need a set of weights that go along with it. And we say X prime is a coreset if for all models Y, the true log likelihood on the left is approximated by the approximate log likelihood we get from just looking at the coreset. So that's just looking at the, just summing over the points in X prime. And we have to add a weight. I mean, just at one level, there are a lot more terms on the left-hand side than the right-hand side. So to get them to be comparable, you'll need some weight. But it's actually a lot more interesting than that. The weights should, one of the most common ways to build a coreset is via importance sampling, where you assign different weights to different points based on basically how critical they are to the model. So in a setting like this, where you have a big cluster and some small clusters, you don't want to choose X prime by uniform sampling, because then you'll just miss the small clusters. So you want to boost the weight of the, the probability of these small clusters, right? So you want to make sure that you hit the small clusters just as much as the big ones. But you don't want your model to get confused about the relative importance of those small clusters. So you put in the points from the small cluster, you put them in with high probability and low weight. Whereas the points from the big cluster, each point gets low probability and high weight. And so the weight is meant to balance the probability of sampling these things. And that's a critical component of importance sampling. And I'm not going to spend too much time on that, because this is really a technique from classical machine learning. It's not, there's nothing particularly quantum about it, but this is, this is one of the standard ways of generating coresets via this tool called importance sampling. And so this gives rise to a hybrid algorithm for machine learning. You have your data set X, you feed it into a classical computer, you get out a coreset X prime, feed that into your quantum computer, and you get out a model Y. So a little more concretely, how do you get your coreset? So, you know, I said you can do it via this technique called importance sampling, where you weight the things in the big clusters differently than things in the small clusters. But how do you know what's in the big clusters? You haven't solved the problem, right? So there's a bit of a chicken and egg. So one way you can do this, and we'll see a few different answers to this. One way you can do it is you first get a crude approximation. So the classical computer gets a very crude approximation y prime. For clustering, such an approximation might be one of these bi-factor approximations, where not only it's not a very accurate clustering, but also you use maybe 10 times as many cluster centers as you ultimately want to get. And this can be used to construct importance sampling weights. Yes, you can, that's right, that's how you can get y prime, is by classical EM algorithm is a way of doing this. So the point is, it can be a fairly lousy approximation. The quality of y prime will not affect the quality of the final approximation. It will only affect the runtime to get there. It will only affect the size of the core set. So use that to construct importance sampling weights, use that to construct x prime, then you feed that to your quantum computer, use Grover or whatever your favorite quantum optimization algorithm is to find the model y. And now you've cut down the cost of the inner loop to be only dependent on the size of x prime. So if x prime is much smaller than x, then you can get nearly the full Grover speedup, or whatever your optimization algorithm is. The inner loop no longer becomes a dominant part of the runtime. And for algorithms like clustering, this is a case where we know good core sets exist. So this whole pipeline where you choose an approximate answer quickly, use that to make importance sampling weights, draw a small core set, etc. This is something that's proven to work for many, many forms of clustering. And this is a promising area for quantum speedup, because the last step is where you brute force over clusterings of your core set. And this, again, doing a brute force search over a combinatorial space is something where Grover's algorithm works without any of these data issues. And that becomes something where a quantum computer can speed up relative to the best known classical algorithm for a big data problem. Any questions about this? I'm skating over the details of importance sampling, but I can get more into that if people have questions about it. Good. So so this algorithm, it's good as far as it goes, in that it speeds up a fairly natural problem. But as a quantum algorithm designer, I find it a little unsatisfactory, because the classical computer acquires the data, processes it, digests it, and gives a small, representative subset to the quantum computer. It's like what the mama bird does. She finds the worm, brings it back, chews it up, regurgitates it. The quantum computer is just like this baby in the nest. Can we do something a little more glorious for the quantum computer? What about some kind of interactive protocol where the quantum computer sends requests back and says, well, I'd like a worm with more calcium, please. Or, maybe dropping the analogy, can you return me a record that tells, of this nature, instead of your predefined importance sampling weights? Can you do something useful there? And so there are many, many ways of doing this. One proposal due to Campbell and Broderick, I'll describe, and there's also this review paper with other examples of adaptive core sets. It describes a, oh, right, so this actually answers the question that just came up. Is there no quantum in constructing x prime? Well, not for the first one I gave you, but for the subsequent algorithms, the quantum computer will play a role in constructing x prime. So the, right, so the next problem I want to consider is, like maximum likelihood, we want to choose the best model. For Bayesian inference, what we want to do is we start with a prior pi0 of y. We still have our log likelihood and our data set, and that yields a posterior distribution pi of y given by this formula. And we want to sample from this posterior. And so this gives us not just the point estimate of what is the best model, but some measure of a confidence interval around it, like how, like error bars, basically. So one fairly general way of using a quantum computer to get an adaptive core set is the classical computer in round t sends a coreset of size t to the quantum computer. Think of t as pretty small, way smaller than the full data set. The quantum computer samples from the posterior distribution corresponding to this coreset. So it's not from the true distribution. The quantum computer doesn't have time to look at all of the data. It just has time to look at this small coreset, and it can sample from the posterior here. Now, how does it do this? Here's a case where instead of doing the square root speedup of brute force search, we can do the square root speedup of something a lot smarter. For example, one way that a classical computer might do this, if a classical computer do this sampling, you might do it via simulated annealing, where you start from a high temperature distribution and gradually reduce the temperature. And this is something where this is a relatively good algorithm, and a quantum computer can get a square root speedup of this. Modulo a few, I should say a nearly square root speedup. I can get into details if you want, but there we're closer to square root speeding up the best algorithm. Yes, exactly. So pi 0, you can view pi 0 either as the prior, or pi 0 is what you get when there's no data, right? Sort of, it's consistent with this pi sub t. And then, so the quantum computer draws a sample y sub t and sends it back, and then the classical computer has access to the coreset so far with the weights, as well as all of the y1 through yt's. And it can use that to update its coreset, to choose the next points to add based on the y1 through yt that it's seen so far. And basically what it can do is it can say, let me try to find a point that is not well fit by the models I've seen so far. So instead of just choosing according to the pre-existing importance sampling weights, say, the models from the quantum computer, what have they missed? Whatever those are, we should focus on that part of the data set. Campbell and Broderick have a scheme for doing this. Since it's essentially classical, I won't go into the details, but this gives you kind of the idea of a framework of how you can adaptively build up a coreset where you're making use of the outputs of the quantum computer in the process of doing this. And then, yeah, so I'm going to move on to a more concrete example. This was maybe a little bit general. I'm going to move on to a more concrete example where we can, have an algorithm I fully describe with a provable performance. This algorithm is sort of a heuristic. Like it's a plausible algorithm. Campbell and Broderick have a concrete proposal, which I just won't go into right now. But it doesn't have a provable convergence time, or rather it does, but it depends on parameters that are hard to estimate. Like the adiabatic algorithm depends on the gap. That's good to know, but what's the gap, right? And so this is something where I think it's a promising heuristic to try, but it's hard to say in general how well it works. Any questions before I go on to a concrete instantiation? Okay, so let me talk about a problem where I can describe how everything works in more detail, but I have to specialize a little bit. So I'm going to specialize to a problem called saddle point optimization. And I'm going to change a little bit my setup. So instead of X being my data set, I want X to be the convex hull of all of my data points. So here are my data points. That convex hull just means the smallest convex set containing them. And Y, my space of models, I'm going to make that convex as well. If you're familiar with boosting, that's a little bit like what happens in boosting, where you're allowed to output not just a model, but some convex mixture of models. And my objective function, f, I want to be linear in x and y. And if I make these assumptions, then I have this minimax theorem. Well, okay, and sorry, the thing I want to do is I want to maximize over y and then minimize over x. And if I make these
I'm sorry, Aram, can you go over the problem statement again? It was a little bit unclear.
Yeah. The problem statement is compute the max over y of the minimum of x of f of x, y.
Right, and x and y are, again, sorry, I missed.
X is the convex hull of a bunch of data points that you're given. And y you can think of as the convex hull of m models that you're given, or you could just think of it as the set of probability distributions over m items. So let me make this a little bit more concrete. So one example of this is a zero-sum game. I mean, the way I've written it, it really sounds a lot like a zero-sum game, where there's an X player, and the X player's strategy are described by records on a hard drive, and a Y player, and the Y player's strategy is given by something you have superposition access to. So, for example, suppose I have some, enormous data set of, possibly fraudulent credit card transactions. That would be X, and then Y would be a set of strategies for identifying fraud. That maybe these strategies are describable by some parameters, so I have superposition access to them. Something like that. So a zero-sum game where on one side there's data, and the other side there's sort of an implicit data set, something I have superposition access to. Another way of viewing this is linear programming. So I want to find a point in the probability simplex, and X is a set of linear constraints. Every point X describes some half space that cuts down the space. It's a little bit like maximum likelihood estimation. You can see for maximum likelihood estimation, I'm doing a max over Y followed by a sum over X. This is a minimum over X. So you can imagine a clustering problem where instead of caring about the average error for any point, I care about the worst case error. So, think about some kind of coverage problem where I want to make sure that no customer has like service below some quality. It's also related to, if you know SVM, this is like SVM using the L1 norm instead of L2. So this is something that's very amenable to these hybrid algorithms. Following, you notice there's a theme here. There's some classical algorithm that we can easily adapt to this setting. And so there's an algorithm from 25 years ago called fictitious play, which I'll illustrate in the context of rock, paper, scissors. So you want to converge to a Nash equilibrium for rock, paper, scissors. The simplest thing, which doesn't work, is just have one player pick a strategy, like scissors, and the other one does a best response. So then the other player would do rock, and then you respond with paper, then you respond with scissors, and you can see it's just going to cycle forever. But if you put in a little bit of noise, it will converge rapidly. So here's how that goes. Here's your payoff matrix, and I've set it up so this is the payoff for the Y player. So the Y player wants to maximize it, and the X player wants to minimize it. And the way it goes is the X player will choose X1 arbitrarily, let's say rock. That will induce some vector of payoffs for the Y player. The Y player will sample a Y1 in a way that is biased towards larger payoffs, but not deterministically picking the highest one. So paper is more likely, scissors is less likely. Let's say that Y1 happens to be paper, the more likely one. Then we go to the X player. That induces a column of payoffs for X. X now bias it towards the lower numbers. And scissors is most likely, and let's say that X happens to choose paper, because that happens with some probability. Now, the Y player responds to the sum of everything that X has done so far. So you see, if epsilon is small, at first the players are bouncing around at random, but the probability of choosing some bad strategy starts to decrease exponentially with the number of rounds. And so it converges pretty rapidly, at least rapidly in terms of the number of strategies. So they prove that the number of rounds you need scales like the size of the strategy space divided by epsilon squared. So the performance with error is not so good. The performance in terms of size of the strategy space is very good. And this is a natural hybrid algorithm because if T is not too large, there are T rounds of alternation. And what do the classical and quantum computers have to do? The classical computer has to sweep through the data set. And for each data point, it has to calculate the sum of the T things that's returned from the quantum computer. So it has to do an order T calculation for every data point, which is not too bad if T is not too big. Likewise, let's say the quantum computer was going to use Grover to search over its strategies. You were already willing to do Grover once. And now what you have to do is you have to do Grover T times with an order T calculation in the inner loop. So if T is not too bad, this is not much more than just the minimum you were willing to do to, to run Grover once with a simple inner loop. So this is a fairly concrete way of an example of an interactive classical quantum algorithm to solve a problem using a large data set. Any questions before I go on? Okay, so I prepared a few other things, but I should probably go through them quickly to not take up too much time. I want to mention, when people say variational algorithms, when people say yeah, okay, so a few questions about this last one. T scales with the size of the matrix, so I assume it's not so big. Well, it scales, there's a log here, it scales logarithmically with the size of the matrix. So, I consider log to be not too big compared to other things in the problem. And another question is, the output strategy is a superposition. The output strategy is a mixture. Yeah, good question. The output strategy is a mixture of all of the things that have been output to date. So, this produces a sequence of outputs x1, x2, dot through x sub t. The final strategy is the uniform mixture of x1 through xt. Okay, so when people think about hybrid algorithms, they're often thinking about variational algorithms. And these look like you have some variational ansatz, so and that looks like you start with some state psi 0, you apply a sequence of given by some parameters t1 through tp. One example is QAOA, so you maybe start with all many copies of the plus state. Sorry, that should be psi 0 with many copies of the plus state. And then you apply alternatingly either the sigma x Hamiltonian or the function that you want to optimize along the diagonal. Or another thing you might do is the variational quantum eigensolver, where you're trying to minimize some Hamiltonian and you alternate different terms in the Hamiltonian. These are all different variational algorithms that you might run on a quantum computer. And the way they generally work is you have a classical outer loop that searches over these parameters, and then the quantum computer is used to estimate the expectation value, basically how good is your approximation. And one thing that's appealing about this is this yields something interesting even for a very simple quantum computer. So you don't you run the quantum computer basically as long as you can get away with, and that defines the quality of your ansatz, and then you search over that. So it's easy for small p. P is the number of parameters here, and it's exact as the number of parameters goes to infinity, because it includes things like adiabatic evolution that will always give the right answer. Of course, that might take exponential time, but at least in principle, this family, it's not going to saturate at some small value. That it has at least the potential of doing well. But at this point, it's so general that maybe you don't have enough guidance to solve it. So one question is, should you be using a 0th order method where the quantum computer's job is to estimate the energy, or a 1st order method where the quantum computer's job is to estimate the gradient, or maybe a 2nd order method where we are evaluating things about the matrix of second derivatives? And I think I don't have time to really get into this. It turns out a quantum computer can estimate gradients efficiently. The cost is barely more than estimating the energy. And in some cases, you have some rigorous performance guarantees, which I think I'm gonna skip. And it turns out that there's a very, very simple example where these gradient algorithms do better than ones that just measure the energy. It's just the Hamiltonian is just a sum of single qubit terms. So super simple, nothing fancy going on. You wouldn't even think that these n qubits even interact, but they do interact kind of via the outer loop of gradient descent. And it turns out in that case that we can prove that first order, that gradient algorithms do better than just direct energy measurements. And I think there's for this case, there's no advantage in going on to second order algorithms, but I think that's an interesting thing to look at in future work. Second order algorithms where you look at the Hessian have not been popular for classical gradient descent because it's too expensive to write down the whole Hessian. But here, I think there's the trade-offs are a little bit different. We're willing to have the classical computers sweat a little bit more to save the quantum computer time. And so one thing that I want to look at in the future, and encourage people in the audience to do as well, is think about ways that that second order methods could further improve these quantum variational algorithms. Now, these performance guarantees, which I sort of went through quickly, or didn't really explain at all, are all in the neighborhood of a local minimum. But the problem with these variational methods, with anything with gradient descent, is how do you even reach a local minimum, or sorry, a good local minimum? I didn't say this very well. How do you find a good local minimum in the first place? And one challenge is that if you just do random initialization, you get something called the barren plateau problem. And this is actually kind of a beautiful plateau, but imagine a very, very flat plateau. That is sort of what the solution landscape looks like. And that makes it very hard to figure out which way to go in. So more concretely, let's say that F is the thing you want to evaluate. It's the expectation value of your Hamiltonian. The gradient of F goes down exponentially with the depth of your circuit if you do a random initialization. Now, one answer to this is, well, random initializations are just a bad idea. What we do with our computers is usually not pound on the keyboard at random. Usually there's some structure to it. And Misha's Lukin's group has had a lot of progress with initialization strategies that are inspired by adiabatic but go beyond it. And my group is looking at some ideas related to this, which they're not quite far enough along to present, but hopefully soon we'll have something to say about it. But it is a challenge for these algorithms is finding a good initialization. And one further thing, this is another, unpublished work from Eric Anschwitz, a student in my group. If you zoom in on the barren plateau, it's actually not flat. It's actually full of teeny little bumps. And he has a heuristic argument for this, sort of in a toy model, and then he conjectures that this should hold more generally. But the scope of his claim, we don't know kind of how widely it applies, but but wherever his heuristic model applies, there should be exponentially many local minima with that are very bad local minima, that they are basically not much better than doing something at random. So not only is this plateau kind of very flat with exponentially small gradients, it has many of these little bumps in it. And numerically, here's an example of what the transverse field Ising model looks like when you just sort of jump in at a random point. You really do see lots of little bumps. So this does not mean that these algorithms are doomed. It just means that there's more work to be done in getting a good initialization. So, and I think it's a little bit like the situation with deep neural networks, right? There's not going to be any general purpose theorem that we can always find a good answer for them. Nevertheless, there are many strategies which empirically cause them to work well, and there are many ways that we can find regularities and get them to work well in practice. So these difficulties are not the end of the road. Similarly, for this recent paper about NP hardness, it's not the end of the road. It just is sort of the first step towards finding better algorithms.
So, sorry, may I ask a question, Aram?
Yeah.
So you spoke a little bit about where the algorithm would run into difficulties. Do you have any heuristic, or do you have any picture of where the algorithm might work well? Not provably well, but if you wanted to look for places where variational methods or QAOA actually works better than classical algorithms, where would you look, or where would you have a feeling that they do, or some sort of picture that they do?
Right, like let's say you just have your system of 100 qubits, you want to try this thing, you don't want to hear about NP hardness, you say, okay, well, what do I try? Give me an idea. I'll try it. I'll see if it works. And so you'd like some guidance about something that's maybe guaranteed to work in some regime, and then you try it somewhere else. And one thing that, one thing that's very appealing is to start with an adiabatic path, because the adiabatic algorithm does work if you take exponential time. And there is, it often does okay if you use less time. There's the next slightly smarter thing you might do. There's something called the shortcut to adiabaticity. There's an enormous literature on various strategies of doing better. That might also be a starting point that you might use. For example, you might use adiabatic where you run at different speeds at different times. There's one thing that I've been looking at, which, when I said I would give this talk, I was kind of hoping I'd be further along in terms of results, but I don't have a slide on it yet. But let me try to describe it. So one case, one thing you might do for a general problem is you might say, let me engage in wishful thinking and hope that my problem secretly has n qubits of decoupled degrees of freedom. So that's crazy. I have some big interacting system, but maybe it has a description in terms of quasi-particles, and these quasi-particles are weakly interacting. And sometimes this is true. So you have exactly solvable models like the transverse field Ising model, which really do just map onto n decoupled qubits. And if you do adiabatic evolution there, it corresponds to adiabatically evolving each of these n qubits separately. But if you're dealing with qubits, you can do something a lot smarter. You can do something like the qubitization technique that people have used for Hamiltonian simulation. And you can do some pulse sequence that will, that will do a better job that might even be, you can say, if I have these many degrees of freedom, maybe I'll do something that if their parameters are in some range, I will do a good job on. And if there's some other range, I don't have any guarantee. And so basically you can do things that are sort of guided by what would work well for single qubit Hamiltonian, and you can hope that works well for your general system. So I think that's one set of strategies you can try. And then another one is getting guidance from one of the things that goes slightly beyond adiabatic is in adiabatic evolution, we often try to stay in the ground state. But we're starting to understand that if you go too quickly and you jump into the first excited state, that can sometimes help you, which is, this is described in this literature on shortcuts to adiabaticity. And so that's something that, that indirectly you can also try with these kinds of methods. And finally, maybe it would take a long time to, there's a paper, I can't remember who wrote this, it was by part of the Google team. And they argue also in favor of basically one further idea that you can do is suppose you want to solve QA/OA. So you want to solve a classical optimization problem. It might be better to still along the way try to optimize for some kind of quantum objective function where you have a Hamiltonian with sigma x terms in it. And the reason for this is if you just try to optimize a classical objective function, then there'll be no control on the phases of your wave function. And so your optimizer might end up having your phases vary in crazy ways. And so putting in a little bit of putting in these sigma x terms might act a little bit like a regularizer and try to prevent the phases from varying in too wild of a way. So anyway, those are a few different ideas, and they're somewhat disjoint. It's I don't have any one clean answer, partly because I don't know, and probably because such a thing doesn't exist. But yeah, it's a great question, and you know, a very important area of future work. I should probably wrap up, right? We're 65 minutes into things. So let me say that my saddle point algorithm is secretly a form of gradient descent. And I'm just not going to explain how, but it's something called stochastic L1 norm mirror descent. So it turns out that the different halves of my talk are maybe not so disconnected after all. I'll mention something I didn't have time to get into, but hybrid algorithms also could play an important role in quantum simulations. There's a big line of research called error mitigation, which is basically you simulate at some parameters and you extrapolate to other ones. That's a one type of hybrid algorithm. Another one is there are these randomized Trotter methods where people have been choosing the terms in the decomposition, maybe just according to the strength of the term, but there's room for making these adaptive as well, for choosing them using an important sampling which would actually look at the quantum state involved. Another way of linking classical and quantum is to do a quantum simulation where you use quantum Monte Carlo for some degrees of freedom and use a quantum computer to do tensor contraction for other degrees of freedom. These are, in each idea I think I would take quite some time to explain, but those are brief sketches of things that you might do in a hybrid way. And so, yeah, let me wrap up by talking about one more form of hybrid computation. After Kasparov lost to Deep Blue, he didn't come up with the idea, but he helped popularize the idea of centaur chess, where there's a human and a computer together. And this example also illustrates the difficulty of these algorithms, because there was a period when centaur teams had ratings that were higher than the best computers. And that period has unfortunately ended. And now humans do not add any value to chess playing algorithms other than, plugging the computer. And so I hope that there'll be a long and fruitful area when both quantum and classical computers will be integral to the success of some algorithm. And I hope maybe some people in the audience will come up with new ways of doing this. Anyway, thank you for your attention.
Great, thank you. Thanks, Aram. So wonderful talk. So let's, if there are any questions.
Yeah, Lin had a question earlier. If you want to unmute, that I think got missed. It was.
Hey, Aram. Thanks for the very nice talk. Yeah, I was basically asking that you argued about the second order methods. And yeah, so they definitely make the classical computers sweat. But as far as I know, they will make quantum computers sweat as well, quite a bit. Yeah, so any comments?
Right. Well, this is an idea for future work, so I have not gotten it to work myself, but let me tell you my thoughts. First of all, there are two ways of making the quantum computer sweat. There's running it for longer time, and then there's repeating it more often. And for our current quantum computers, there's just a hard limit to the first one. And maybe running it more often is painful but doable, but running it for more time is just simply impossible if our noise rate can't be brought down.
Mm-hmm.
So it might be acceptable to run a quantum computer a ton of times. Second, I think there is room for using the classical computer to do things that would be way too expensive for a normal gradient descent thing. Like, I could use the classical computer to solve a semi-definite program to find an estimate of the Hessian based on a few measurements of the quantum computer, right? So, think of the classical computer should be like waiting hand on foot on the quantum computer. Any data that comes out of the quantum computer, the classical computer should work super hard to interpret. And so if I have to solve a semi-definite program every single time the quantum computer finishes a run, that's probably still a good use of my resources.
Yeah, you have to control your Monte Carlo error. You have to run a lot, right? So to make that Hessian useful.
Well, what I'm thinking is not yeah. So what I don't know is if you could mitigate that by running the classical computer for longer. So if you think about like LBFGS, you're making gradient measurements, and you're using this to infer some like really lousy approximation of the Hessian, right? So you're not making a ton of gradient measurements. You're not making nearly enough to fill out the full Hessian. So that's kind of what I'm thinking of here. The quantum computer would make a few gradient measurements, and the classical computer would, you know, approximate it, use some kind of semi-definite program or other convex program to get some, you know, some suitably regularized thing. But, you know, you're absolutely right. We have to do something smarter than just running a bunch of times and trying to estimate every single entry of the Hessian, because that, you know, that might be really too many repetitions.
Okay, thanks.
Okay, yeah. So I see there's both a chat window and a Q&A window. Let me go through. Yeah, or just how should we do this?
Yeah, no, please do. And I should just say that I also posted on chat or the messages the Gather Town link for people who want to, you know, who want to go there as this discussion comes to an end. Right?
Yeah, I guess once we close the Zoom window, then I'll show up at Gather Town or something, right?
Right.
Okay, so yeah, let me go through the chat first. What I mean by transverse field Ising model? Ising model means that there's ZZ, nearest neighbor ZZ interactions. Transverse field means that there also is a sigma X term. And just go to Wikipedia for transverse field Ising model, and I think it'll explain it pretty well. And for the two-player games, no, there's no quantum superposition. At the end of the algorithm, the strategy, you know, at every round, the classical computer is output x1, x2 through x sub t, right? And the quantum computer is output y1, y2 through y sub t. These are classical strings that have been output. And so at the end of the day, the classical strategy is just the average of x1 through xt, and the quantum strategy is the average of y1 through yt. So there's no superposition at the end. And the quantum computer, for each run, it does some search, and then, you know, you assume that the thing is fully decohered. You reset it, you you know, whatever, vacuum out your lab, whatever, and restart it. Is there a limitation to QAO in terms of locality? If they don't see the graph, that's not so good. Yes, certainly that's probably true. But, you know, it doesn't take too long to see the whole graph. Oh, some people have answered these questions already. So, okay, so is the calculation of the gradient itself done in a quantum way? So I kind of went through this too quickly. Let me show you how to do it. But yeah, so this was a point of our paper. One way you can calculate the gradient is with finite differences, right? So then the quantum computer is just estimating the value of the energy, and you just estimated at two nearby points and you subtract, and that's going to give you your gradient estimate. And some of the early works on variational algorithms suggested that this was a better way to go, because when you measure the energy, there are many commuting terms, and you can measure them all at once. And when you measure the gradient, you cannot, each run of the quantum computer just estimates one term in the gradient. And so it was maybe a little surprising that you're still better off doing this. And I'm just going to leave up on the screen what is the quantum circuit for estimating the gradient. I won't run through it, but, you know, there is a simple thing to do, and it basically is the same as the normal algorithm. It requires one extra qubit, and in a few places you have to do something in control. So it's barely more effort for the quantum computer than to estimate the energy. For the bad local minima, you know, yes, maybe there may be some averaging method to get around it, you know, simulated annealing. I'm not saying this is a showstopper. And you know, many of the issues that come up there are similar to the issues that come up in neural networks. So it's not a you know, it's a well-studied problem where we don't have a unique quantum answer to. We're grappling with many of the same issues. And okay, I think I've answered most of the questions. Anyone feel like I haven't answered their question or want to ask a new one?
Just to follow up on the question I asked before, would you comment on, I mean, there have been some papers saying that QAOA, for example, this hybrid quantum classical algorithm doesn't really beat classical algorithms for things like max-cut and SAT and the, you know, other combinatorial problems. Any comments on that?
Well, the one for, yeah, so those are, yeah, so there are two different issues. There are a few different no-goes that have come up for QAOA. The ones, there are two issues that come up. There's symmetry and locality. So there's a paper by Sergei Bravi, Eugene Tang, maybe Robert Koenig, and one other person, where they refer to symmetry as a problem. And there's that one also talks about a limitation by about locality. I mean, I think probably the simpler one is if the depth of QAOA is too low, then you can't even see the whole graph, right? So if you're running it for less time than it takes for a signal to get from one end of the quantum computer to the other one, how are you going to solve a problem that depends on the whole thing? You know, I think that's a valid point, but you'd be running QAOA in such a limited, like if you're running for such a low depth, you probably wouldn't expect it to do too well. You know, yeah, so I think these no-go theorems are interesting, but basically they apply to a very restricted version of these variational algorithms. You know, there's a sense in which, you know, I think the thing about variational algorithms is there's a sense in which they're fully general. Like suppose I have any quantum algorithm to solve max cut, and that algorithm is a sequence of gates, and I run it. Then you know what I can always do is I can just say, well, let me look at the gradient if I mess around with each of these individual gates. And let me just take a little step to improve the objective function, right? So for any algorithm that I start with, I can take some gradient steps to try to improve it. And variational algorithms are so general that they include basically taking any possible algorithm and taking gradient steps to improve it, right? So there's, you know, like, it's almost vacuous to talk about like variational algorithms in general. Like really, there are two steps. There's, I need to find a good starting guess, like a good starting heuristic. And that can come from adiabatic or shortcut to adiabaticity or you know, some other idea that might exploit some structure of the problem. And then I iteratively improve it via some sort of gradient descent. And the first step is fully general. Like I'm already starting with like my best possible guess of how to begin. And then, you know, yeah, why not improve it via gradient descent? So, you know, there's a sense in which like we should absolutely be trying these variational algorithms, but it doesn't say like, if you just say this is a variational algorithm, like you haven't really said very much. You know, there's quite a lot of room to narrow things down. So it's, you know, on the other hand, it's very hard to like say anything definite about them without starting to make assumptions. So that's why our gradient descent paper, we had to focus on like a very simple problem in order to like say something provable. I mean, it's a little bit like neural networks there, right? So neural networks are a Turing complete model of computation, and they're differentiable. So you start off with some maybe initial guess of how to tackle the problem. Maybe your thing is informed by some intuition about the structure, like, oh, it's an image, do a convolutional network. And then you set it up so that you can take derivatives, and so you can do gradient descent. It's hard to say stuff in complete generality. Instead, it's sort of like a good framework for thinking about algorithms. But sometimes you have to get more concrete to say more specific things.
Can I ask a question more on the first half of the talk?
Please, yeah.
Yeah, so it seemed like the main idea there for the hybrid nature was, you really want to be smart about what classical data you're using. So in terms of either using importance sampling or finding a way to iteratively do that update. I guess the question I have is more about the application, because it seemed like the problem was more along the lines of parameter estimation as like along that line of problem. And I was wondering if you had applications in mind for like what you would use a quantum computer to like solve for that.
So in the archive link, the second paper here, I spell out a few examples. There are 3 algorithms, so let me go through each one. I guess for the non-adaptive coresets, I think clustering was the main example I had in mind. And clustering is quite general when you think of all the possible metrics and so on.
Mm-hmm.
For the second one, I was thinking of some sort of hard Bayesian inference problem. So, you just have some gnarly model and you have some data points and you want to sample from the parameters. I guess that's what you said, of parameter estimation.
Mm-hmm.
And for the third problem, it's like that, but you have to have some reason why you care about minimax. Like you have to care about, why do you want to do a good job on all of your data points and not just sort of on average? Like, why is it unacceptable to miss any one data point?
Mm-hmm.
And so I think for like security type games where you're interested in possible ways to hack into a system or possible ways to commit credit card fraud, where there's some sort of adversarial element, you really want to make sure that you do an okay job on all of the possible ways, because an attacker would just shift resources to some undefended approach. Or if there's some sort of coverage problem, like, I'm doing a vaccination campaign and I don't want to miss any one subgroup. I want to make sure that I get decent coverage everywhere instead of just sort of, on average doing well. Yeah, does that answer? Yeah, those are the sort of applications I had in mind. Is that?
Yeah, that's helpful. I guess I was just wondering if, I mean, obviously, like you said, the applications of those problems are quite broad. I guess I was wondering if there was any intuition for why a quantum computer would be better at doing those tasks, but maybe that's.
Well, I mean, I think for in each of those tasks, there's some point at which you're doing a brute force search, or where you're doing simulated annealing, and so.
I see. Okay.
At that point, that is you have a quadratic quantum speedup. Now, I wish you could get more than a quadratic quantum speedup, but yeah. Right.
So Aram, can I ask you a different, sort of a funny question? So, well, one could say that that we formulated optimization problems because of, in the classical world, in terms of what we want to do, or what processes actually, natural processes we think of as doing. So when we think about variational algorithms, is there a different kind of problem? Is there a different kind of objective function we should be thinking about?
You mean like other than like a classical, like other than the one that you would want for a classical optimization algorithm?
Yeah. So, is there, if we were thinking from scratch without any bias, and we were saying, look, as you were saying, well, look, what's a variational algorithm? You sort of look at what the quantum world can do. You think about, well, there's the adiabatic algorithm, there's this, there's that, right? So you say, well, what's natural to do in the quantum world? And now let's add, let's sort of take some tunable parameters out there, and then let's tune them using a classical computer, right? So
right. You definitely need an objective function,
right? But are you sort of led to an objective function almost inevitably, or is that our classical sort of lens, glasses looking through these?
Oh, I see what you're saying. Yeah, you're saying, could you have a goal that's not summarized in terms of a single objective function?
Yeah.
Like sometimes you want to, instead of solving a problem, you want to do some sampling problem, for example.
For example, yeah. But,
I mean, maybe you have something in mind but for me, I mean, I think like the quantum computer, that's kind of why I started with this thing about the input models. Like at the end of the day, the quantum computer is going to solve the same problem that the classical computer is going to solve, but faster. Like there's no, it's hard to, unless there's unless you're talking about some kind of communication model, or, where once there's multiple players, then you can talk about privacy and all kinds of other things can come into it. But if you're just if you just have a computer on your desk and you're putting in some input and getting some output, I can't imagine just like categorically how what is inside your computer would change your goals of what you want to compute. Like if you wanted to compute some random sampling problem, you might have wanted to do that with your classical computer already, right? But maybe I'm just, could be a failure of imagination by me, but.
How about TSP as hard, NP hard?
Sorry, what about what is hard?
Traveling salesman problem as NP hard.
Mm-hmm.
Maybe the quantum computer can do better. Not only faster, just.
Yeah, I mean, like you could say, can you improve the approximation quality, right? So not just, but.
Maybe do the impossible now. Do it. That was the gist of the question. Can you enhance your horizon of problems?
I mean, the point is, anything the quantum computer can do, unless you're talking about multi-party where you could really get into privacy or security or, compression, whatever. But if it's just one computer on your desk that you feed an input to, and you get a classical input to it and a classical output, because a classical computer can simulate that with at most an exponential slowdown, right? Definitely exponential slowdown, and in a lot of cases better than exponential. Then whatever's possible quantumly is also possible classically. So at some level, we're always talking about a speed up, right? The question is just how much of a speed up. It's like
okay, that's good enough. Great achievement.
It's like if a student says, will you give me an A if I give you $1 million? And I say, oh, we could talk about that. And they say, well, give me an A if I give you $10. And you're like, come on, what kind of person do you think I am? And then they say, well, we already established that. The question is just, what is the price? Right? What is the advantage of the quantum computer? At some level, it can only be speed. It's just a question of like, how much is the speed up? I don't know if that was the right analogy for that.
That's a nice one.
All right, should we get cookies and gather.town?
Yeah, I think we should do that. Let's let me end the recording and